Hello and welcome back to the lab. Today on the bench is a Tektronix Type 576, but this is not a repair video. This particular unit was restored and repaired very early in the channel. I think it was within the first 10 videos that I put out on YouTube. So restoration was quite successful, and we have the unit here in alignment, calibrated, fully functioning, and ready to rock and roll for the lab. The two units that I did that video on are not on the bench, they're hiding over in the corner. But for the bench, we have the 577's smaller brother, the 576's smaller brother, the 577, which lives on the bench right next to the soldering equipment. But this video is some curve tracer basics. I've been trading emails with a number of people, getting started with one of these units, seeing them for the first time, trying to figure out what's going on, what all these controls are doing, and how to get curves on the unit. Also, how to see if their unit's even functioning. You get one of these units from secondary market, and is it even working? How do you get started at least showing some transistor curves and making sure the unit's functioning prior to repair or after repair? So, without further ado, let's talk about curve tracer basics, and we will get some waveforms thrown up on here shortly. So what is a curve tracer? Well, for those familiar with an oscilloscope, pardon the camera movement, because we'll be using this here in a little while. That's why it's on and warming up. An oscilloscope gives us voltage and amplitude with time on the horizontal. So we have voltage on the vertical, time on the horizontal. With a curve tracer, we have voltage on the horizontal, current on the vertical. So one of the really nice things about this particular unit is it can measure very small currents, and it can also measure very high voltages, especially when you do something dumb like this. No, I did not show how to do that in the videos, because this unit will go up to 1500 volts collector at 220 watts at the highest power. So this unit can give you a pretty decent, if not fatal, shock just from the front terminals alone, not even having to take the covers off. So with all that being said, as always, take care, and we'll get into it. So the unit that this individual viewer of the channel has at his disposal is a 575. That is the 500 series equivalent of a transistor checker. The 570 is the tube version. I am looking for a 570 for the lab. I want to get a 570 on camera. I have not found one yet that has been in restorable condition. The few that I have seen, the CRT's gone, they're gutted, they're in extremely rough shape. So if I do get a viable 570, that will come up to the channel. But for the moment, we are going to talk about the curve tracer basics through the lens of a 570. There's a lot of controls that do the same thing. There are some additional controls on the 575, which I'll talk about, and there are some controls that were omitted from the 575 to the 576. At its heart, the curve tracer is essentially a power supply that will apply power between the collector and the emitter terminals on the front porch. So in the NPN version, we do have a positive collector and a negative emitter. In the PNP version, we would have a negative going collector and a more positive emitter. It's essentially ground, because it bounces the device under test around ground for this unit. For two-terminal devices, you only need collector and emitter ports. The 576 adds Kelvin sensing. We'll use an antenna. So we have collector Kelvin sense and emitter Kelvin sense. There is no Kelvin sense for the base drive of the 3-terminal device. So if you're testing a 3-terminal device, you would have collector, base drive, and emitter. The two primary controls that run the collector would be the max peaks volt control, along with the series resistor, and this control down here, which is the variable collector supply. So what the way these work is this knob, turning like so, would set the maximum peak voltage on the collector terminal. So in this position, if I cranked this all the way up, we would have 350 volts here with a 140 ohm series resistor. That's current limit resistor to essentially limit out the power that this unit is putting out. The controls on the 575 that these would be similar to would be the peaks volts control and the dissipation limiting resistor. So we have peak volts and dissipation limit. So if you need to test something small signal, we can do a 15 volts peak, pull this all the way back to a 650 ohm series resistor, and that'll give us a 0.1 watt max out of the collector terminal. I can even go a little bit lower, so like a 65k ohm. I've done that for testing incredibly sensitive devices like tunnel diodes, things like that. When I've tested the tunnel diodes in, say, a 284, D180 is a very sensitive component, and you don't want to burn it up by hitting it a little bit too hard, but you do need about 20 milliamps to get that TD excited. In the NPN position, we'll set this in here, and we'll take a look at this scope here in a minute, but let me get some test equipment set up. Okay, one thing that was causing me a little bit of problems in the beginning was I had it on 300 microseconds for pulsed steps, which automatically puts the unit in DC mode. I want it in normal sweeping mode to show what I want to show, so I need it to be in the steps setting, which sets it up for sweeping, which is what we're looking for. So when setting up the curve tracer for an NPN, your start point is in the bottom corner. PNP, it would be upside, top right, because it would be inverted. That's what positive going collector, negative going collector. The invert button. So if we switch this to PNP and we hit invert, that'll put the curves down here like you would expect. If you are just grabbing one of these from the secondary market, especially the 576, take a look at these 3 switch packs. They give all kinds of problems with signals. So if a quick test is take it and shake it. If you're shaking it right here and this is jumping around and going crazy, or you're down here and this is jumping around going crazy, or the invert, the switch needs to, these switch packs need to be cleaned. They do clean up well, as we can see, but that is a sore spot on the 577. So I've got a max peak volts set for 15 volts. We'll back out the series resistors because we don't need it that high because we're just feeding into a scope. And I'm going to touch the oscilloscope to the collector, so we're going to take a look at what comes out of the collector. Now this is in sweeping mode, so if I turn the variable collector supply up, we'll see a line start getting drawn. I have the focus turned way down so we don't burn the tube in. The tube is nice and healthy on this one, and I would like to keep it that way. So we'll take a look at the 7603. Speed this up a bit. Now what we're going to do is I'm going to touch the collector supply right here, and we're going to dial this up, and what we're going to see is not what I want to show, but that is what I want to show right there. So this is not static DC. It's a little slow for this scope, so I'm going to move up to the Rigel. So here is what we have coming out of the collector on a 576, and I'm sure the 575 as well. It is not DC which is important. This is actually how the unit is developing the sweep across the display. This is at a frequency based on your line voltage. So in my area of the world, it's 60 hertz. And that is fed into the collector transformer, which is an isolated power supply on the unit. So it is derived from mains voltage. But the ground of the front porch is not the ground of the instrument chassis. It's a floating supply. All of the current limit resistors and everything like that is internal. One of the things that I gathered was trying to happen was measuring the accuracy of the DC coming out of the supply. Well, the problem is the 575 does not have a DC function. The 576 does. There is very small smoothing capacitors in the collector supply, so I can get rectified DC, although there's not a lot of capacitance behind it. It's filtered DC. It is rectified. It's actually full bridge rectified, but it's not filtered, which is by design. So the measurement on, if you just took a meter between collector and emitter, it's going to look a little funny because it's not a static waveform, or it's not static DC. It's a dynamic waveform coming out of the collector supply. This is normal. So I have a DMM switched in across the collector and emitter supply at 15 volts, and we're going to crank it up and see what happens. So going from 0 to DC, not DC because it's at 11.6, which is accurate. Because if I use the measurement functions of the scope, the meter is actually very confused right now. So the scope said we had 16.6 volts peak to peak at 120 hertz. That's to be expected with fully rectified AC. The RMS voltage of that was 5.4. Well, this is a true RMS voltmeter, so we got some weirdness going on. But we know the 576 is 100% working. So the reason this doesn't work is because of the meter being confused on the measurement. It's not expecting unfiltered, rectified but unfiltered power. So if I switch this to positive, which will kick it to DC mode, nope, I have to flip this. Now we agree with what our scope amplitude was, 16.2. So the only difference was I threw a capacitor in there when I switched. I cannot get them both in the shot at the same time. We have a DC control. Now what that did to the display, let's give us some brightness on the tube. So when I switch to DC, we have a dot here, but if I switch it to normal, we have a line. That's because of the sweep of the collector. So you can't measure this with a DMM without putting a capacitor across it and rectifying that a little bit. I would not recommend putting a capacitor across those terminals without an appropriate switch and discharge resistor. You can get some spicy voltages out of this. Remember, this goes up to 1500 volts. Do not want to put a 1500 volts on a capacitor and then grab it. That's a bad idea. So that's what's coming out of the test terminals, and we're only doing a 2-wire measurement. We haven't even done any base drive yet. I have the collector set to sweep, and I have it all the way shut down to 0. So what we're going to do is we're going to measure the input resistance of my DMM. Now, this 576 is capable of doing that, which is kind of nuts. We have a collector voltage of 2 volts per division, so every square division on the screen is going to be 2 volts across the collector and emitter terminals. For current, I have it set to 1 nanoamp collector to emitter. I set this up just to see if it'll measure the input impedance of a DMM, because the input impedance is pretty high, but I also wanted to talk about why, when the dissipation resistor was changed on his unit, nothing really happened on the display and nothing happened on the meter. So what I'm going to do, we're going to crank this up. So what's happening now is you can see right there the meter switched. So the meter's in its lowest range at the moment, and the voltage is climbing. So right there we have about a nanoamp of current. Well, 2 nanoamps of current, really. No, a nanoamp. So we have about a nanoamp of current. There's some balance issues in the amplifier. And we have 1.335 volts across the meter. So what we're going to do, when the meter kicks up a range, this line is going to flatten out. Essentially what that's doing is the meter's kicking into a higher impedance, so we have less current flow, which will happen right about there. So we just dropped down, so our voltage is now 2.5 volts. The meter kicked up into a different range, and so we have a different current flowing between collector to emitter. So very sensitive unit. Now, because we're on the 1 nanoamp range, this looks kind of funny. The way you would take this measurement is you take the average of the lines being at 1 nanoamp. We have some DC looping capacitance, which can be adjusted with this control here. I can expand it out. This, you want to actually null it for the least amount of spread, so the flattest line you can. And then the measurement is actually the average signal that you're seeing. So you kind of ignore the top side and the bottom side and you go with whatever point A to point B is straight across. The reason the dissipation resistor, when it was changed, is you can imagine a resistor right here in front of this red lead coming into the collector. So I'm forcing this current through the input impedance of the DMM, which is about 20 megohms. So if I have a series resistor of 0.3 ohms, but my impedance is being set by the 20 megohm in series with the meter impedance, changing from 0.3 to 1.4 is going to have no effect. It's because the current is being set by the meter itself, in this case the device under test, not by the curve tracer. If I put a resistor across here and then I change the series resistor, you'd see a voltage drop and it would current limit, so it wouldn't burn up the resistor for what I was testing. There's not enough current flowing through these meter leads for any of these resistors down here to even matter. So that's why nothing was seen, and there was no difference when the dissipation resistor was adjusted. Now, for the 576, if I wanted to do a DC measurement and not have any looping capacitance or anything like that, I could kick it to DC. We could go, there's 2 volts, 3 volts, 4 volts, 5 volts. We'll dial in the focus here real quick just to see. Don't want to torture the tube. 5 volts, which is really 7.9. 2, 4, 6, well, 8. So actually, yeah, that's right. So 8. So actually, my count's wrong. You're seeing the capacitor discharge now. That's what's actually going on. And the meter just changed ranges again. I can hear the relays click. That's why it's jumping around. This is how sensitive this unit is. So we have 2, 4, 6, 8 volts, 9 volts right there. We'll call 9 volts 1 nanoamp through the meter. There's 10 volts, 12, 14, just over 16. So the meter's only drawing about a nanoamp and a half through its input impedance, which is fairly impressive because I'm not using any of the fancy meters. To be our 3-terminal test device, we had some 2N2222s decide to volunteer for the honors, partially because I have an entire wheel of them, which is kind of bonkers. There are 2,000 transistors on that wheel. I'm going to end up working on some wheel storage, so there'll be a video on that coming in the future. I have some things on order. So I hope we have some cool stuff going. We'll use the DCA Atlas Pro to check pinout. Blue is the base, so base is middle, and then we have... Okay, we do have collector base emitter, which makes it easier to get in the test fixture. So we have our 3-terminal device under test in the test fixture. We're going to apply a collector voltage, which is going to sweep. We're going to have the emitter, which is essentially ground. And then we're going to apply base steps to this. Now the steps are set by this control right here. Now you have 2 settings on here. One of the ways this differs from a 575 is the 575 has series resistors in the step voltage range. The 576 did not. They took that out. But I have a lot more amplitude steps that I can go. I can go from 50 nanoamps all the way up to 200 milliamps a step. So we'll start with, say, a microamp a step, and we'll get a step family of, say, 5 steps. No step offset, and we're gonna zero the offset, so we're not gonna do series or aiding. And we'll go with 2 volts on the collector. We'll go to 50 microamps on the vertical. So that means each grid square on the display is going to be 50 microamps. We're going to have each line for the step family is going to be an additional 1 microamp of base drive, and the length of the lines across the display are going to be the voltage across the device. So we'll kick it into test. Okay, so we have a spot, a nice focus spot, and we'll kick this over into the left test position because that's where we have our device under test. And we are way, way too sensitive. But we're getting curves. So what we need to do is come down. There we go. And there is our family of curves. So I needed to come down to 200 microamps per vertical division. 50 microamps was way too much. But, so between each one of these lines, we have an additional 1 microamp of base drive into the transistor, which is timed by the unit to the sweep of the collector. That's how the traces stay stable. So this allows us to match devices, do all kinds of things. You can put a second one in the terminal, switch it back and forth left to right, do current matching, do load lines. There's a ton of things you can do with a curve tracer. We can also see if we can hit breakdown. I'm going to go look at a data sheet real quick. Okay, well, data sheet says 40 volts DC should be about breakdown for this transmitter, so we'll kick it up to 75. We now have glowing red lights of danger. We're also going to kick this up to 5 volts on the horizontal, and the vertical will leave at 200 milliamps, or microamps. So what we're going to do, turn up the intensity here real quick. One of the things I like about the 577 that the 576 doesn't do is when you have the collector control all the way down, it dims out the tube so it doesn't burn in the common spots, but that's okay. So we're looking for breakdown voltage. So there's 5, 10, 15, 20, 25, 30. Okay, I can start to see at the highest current drive, it's starting to kind of curve up like this. That's where the transistor's starting to break down. So we have 5, 10, 15, 20, 5, 10, 15, 20, 25, 30, 35. Now we're starting to get breakdown all the way down here. So all of these are starting to curve up. Breakdown and zoop. Now the transistor's in breakdown. So you would not want to use it in this region, but we also didn't damage the transistor. We pushed it a little too hard, not crazy hard, but there was enough current limiting that there's enough current control, I should say, that the transistor didn't get damaged. Now, what will happen is for the series resistor, if we were testing a very delicate part and we wanted even more control, we could back off the series resistor to here, and we're starting to get a reduction in voltage. So the series resistor is kicking in and is limiting the peak voltage going through the device under test. So if I come all the way down here, we can really see, I haven't changed anything with the voltage going through. As we can see, the bottom trace is still where it should be, but now we're seeing the effect of that current limit resistor holding back the current at the higher amplitudes. So that is how that works. For PNP, everything is exactly the same. It's just reversed. So instead of having a positive going voltage on the collector, you'd have a negative going voltage, and the curves would actually come down from the top as opposed to up from the bottom. Or you can use the invert control, because I can push this. So that's what a PNP would look like, unless you use the invert control, in which case that is what a NPN looks like. Now that's very handy because you can do matching with PNP NPN pairs, looking at it a number of ways. If you have a circuit, say an audio amplifier or something like that, that really would benefit from a matched pair of transistors. A lot of tech scopes, certain trigger transistors, things like that, they run in matched pairs. So there was quite a bit of matching that was done to get the dynamic bandwidth so high on the 400 and 7000 series scopes. Lots of that. So I hope that answers some questions about curve tracers, their function, how to set them up, and use them effectively and safely in the lab. If you have any questions, I read all the comments in the description. I read all the comments in the video below, and I am hanging out there with all of you guys between videos. Check out the Patreon page if you would like a little bit more of my content. They are 4 videos ahead at this point. There's currently nothing behind the paywall, so everything will eventually come out on YouTube. However, Patreons are seeing the videos about 4 weeks ahead. So with that, if anybody has any questions, please reach out. If enough people ask the questions, we will make a video about it. And with that, as always, more is on the way, and I will see everybody in the next video.